In this video, we'll use factorial, double factorial to generate the Taylor-Maclaurin series sum of the formula 0.5 times square root of pi times ERFX over the values of x from -2 to +2, which is, we begin with the formula, the summation of a times x to the power 2n plus 1, where a can be a1 or a2, and the value of n is from 0 to infinity. So starting from 0 up to infinity. We continue with the a1 coefficient, which is our formula, minus 1 raised to the power n. Our n is from 0, that is f3, to f16, or f19, divided by the first part. There are two parts of the denominator, so factorial of n, so f3 to f19. The second part, the quantity 2n plus 1, so the quantity 2 times n plus 1, and enter. So we have completed the factorial coefficients. Continue with the double factorial coefficients, which is our formula, minus 2 to the power n. There are two parts, so minus 2 raised to the power n. That's the first part. The second part, this is double factorial. So factorial, double factorial, 2 times n minus 1 divided by, there's only one item at the denominator, that is factorial, 2 times n, so 2n plus 1, 2 times n plus 1, and enter. Their values here are exactly the same, except for the first item. We'll correct that. So using the if statement, that is if n equals 0, 1, otherwise calculate. Now they're exactly the same. We continue with the expansion, which is our formula, series sum of the x values raised to the power 2n plus 1. 2n plus 1 starts from, at n equals 0, 0 plus 1, so it starts from 1. Incremented by, at n equals 1, 2 plus 1, 3, so 2 times 2, 4. So 1, 3, 5, 7, 9. So the increment is 2. And the coefficient, we can start with the double factorial. And we'll chart this. We'll use this scatter chart. And use row 1 as header. For the series, show the trend line. Polynomial to the 8th degree. For the label, use the equation. For the legend, position at the bottom. So here's the trend line and polynomial of the formula of the error function. This is the expansion. We continue with the expression 0.5 times square root of pi times ERFX. So we start with ERFX. So our formula, ERF of the x values. There's no trend line or polynomial, so we change that. Series, trend line, polynomial to the 8th degree. For the label, use the equation. Now we have the equation. We continue with you calculate this polynomial regression coefficient using LINEST. To do that, we complete the LINEST matrix, starting with the power transpose 0 to 8, and the elements of the matrix, array formula, of the x values raised to the power 0 to 8. Now we can use LINEST. That y and that x. And the formula, so array formula or LINEST. LINEST data y and data x. Now we modify the ERF expansion. So there is a square root of pi. So we multiply this by square root of pi. Square root of pi. Enter. Next there's a 0.5. So we multiply again with 0.5. 0.5 times. Now they're all in the same trend line. The data sets are almost the same, except for an error outside 0. And the polynomials are identical. Let's compare with the polynomial regression coefficient. Coefficient of x to the 0, 0. Coefficient of x, 0.997. Coefficient of x squared, 0. Coefficient of x cubed, negative 0.313. Coefficient of x to the 4th, 0. Coefficient of x to the 5th, 0.0696. Coefficient of x to the 8th, 0. Coefficient of x to the 7th, minus 6.54 times 10 to the minus 3. Coefficient of x to the 8th, 0. So that's because we use the double factorial. We change this. Instead of the double factorial, use the factorial. We will use the factorial. Enter. We still get the same polynomial regression coefficients. The polynomials are still identical. The trend line, they're still on the same trend line. And the data sets remain the same. This completes the use of factorial and double factorial to generate the Taylor-Maclaurin series sum of the ERF function, where here it is multiplied by 0.5 times square root of pi.